because I forgot it. You get an extra little break. Not a break, but. So, I always ask students, before we start, what they think, what's the first word that comes to mind when you think about learning chemistry? And don't blurt anything out. But, if you have a phone, or a computer, or a tablet, you can either go to that website. If you go to the website, they're going to ask you to create an account. It's free, but you have to create an account. Or you can text 128253 space and then one word and send it to 37607. They don't charge you, but if your phone company charges you per text. It's completely anonymous, so if you don't want to do it or you can't do it, don't worry about it. I won't know who does and doesn't do it. Okay? The one word that comes to mind when you think about learning chemistry. Now I can log in, see what people. So if you haven't sent it in yet, the numbers are right here. Experiments, explosions, experiments, fear. I don't know if it's fear of the explosions or fear of chemistry, the course. Medicine, molecule, hard, one hard. It's not bad. A lot of times you get, when you look at it, the bigger the word is, the more people say it. And so a lot of times, smack in the middle is hard, right? So I asked before everybody's here, how many people have taken chemistry at some level? Okay. So apparently the people who took chemistry were the ones who came in towards the end. I don't know why. Because before it was about half and half. Now it's about 90%. So to me, chemistry is a subject that once it clicks, it clicks. And I understand that for some of you, it's going to take a long time to click. And for some of you, it may never click. Okay? How soon it clicks will determine how much work you have to put in. Okay? If it clicks early, great. You're probably going to get through without a whole ton of work this semester. But if you're someone who doesn't do well in science, never taken chemistry before, and it just doesn't make sense, we're going to have to do a lot of work. Okay? That would just be honest. Okay? We need to work together to get you through here. Okay? But with the work, we will get through it. Okay? And so I don't think this class is something that if someone really tries at, they shouldn't pass. Okay? I think the way the course is set up, and I don't mean that to mean I don't just hand out passing grades. I don't. I don't want to do that. I want to make you learn what you need to learn to get that passing grade. Okay? And it's my opinion that if you put the time and work into it and work with me, you can get that amount of knowledge to get that passing grade. Okay? In the time, this is my 5th semester teaching. In the 4 semesters I've taught, there hasn't been a person that didn't pass that I can't point and say, you missed these whole group of classes. You didn't come to class, you didn't do these assignments. Okay, there's always something. If you come to class, you do the assignments, and you talk to me, and you help me work you through it, you should be okay. Okay? Now we can get to our lecture. So, Wendy's question 4 was, what is chemistry? So, somebody wanted to give me a definition of what chemistry is. What would you tell me? A bridge to physics? Did somebody say matter? Matter and? Energy. Yay, we can read. So yes, chemistry is the study of matter and energy. A lot of the principles are physics principles. I mean, when you really learn a lot of different science subjects, physics is the one in the middle. Because physics dictates what the molecules and atoms do, and what the molecules and atoms are determine what happens in biology. So physics is really the root of all. So, seems simple, right? Semester done. Final exam, good to go. Matter and energy. We have to figure out what matter and energy are. Because you probably have a vague idea, but if you wrote it on the final exam, it would not be pretty. Right? So matter is anything that occupies space and has mass. So you know what occupying space means, right? But having mass may not be as obvious to you. Energy is not matter. Okay? Things like heat and light, they don't occupy space and they don't have mass. When you get into quantum mechanics, yes, they do, but this is definitely not quantum mechanics. Okay? So in this class, energy does not occupy space or have mass, so it is not matter. Anything that exists is matter or energy. If it doesn't take up space and it doesn't have mass, it's energy. Everything else, if it takes up space or has mass, it is matter. Take a look at this picture. What types of matter do you see in that picture? People?
Cars.
Cars?
Light. Buildings.
Lights? Buildings? Trees? Is there matter there that you can't see? Gases, right? The air. Air is matter. It has mass, it does take up space, it's just invisible to us. So it's there. What about energy? What forms of energy are in that picture?
Light.
There's light.
Chemical.
What do you mean chemical energy?
So like pollution. I guess gasoline. Gas.
Yeah, so we'll talk more about chemical energy. Essentially, gasoline has stored chemical energy. Stored in the molecules. When you burn the gasoline, it releases it. So I want to clarify, I said light, but I said lights before. And so the lights themselves are matter, but the light coming off of them is energy. Okay? What other energy is in there? Radiation. What they're walking, what does that mean? Anybody, what kind of energy do you have if you're walking? You have kinetic energy. Kinetic energy is energy of movement. Don't worry about these words, we'll come back to them. They have their whole own lecture later on. What else? Anything else you see?
What radiation
There's what kind of radiation? There's UV radiation there, right? Technically, visible light is also radiation. I mean, there's also, when you think of radiation, you think of like nuclear power plants and stuff, right? But you've heard of radon, right? Radon can give you lung cancer. It's radiation. There's probably some radon here, so there's radiation. There's also potential energy. Can anybody explain to me where there's potential energy there?
Everything's hanging out.
Right. So potential energy, again, we'll talk about it in more detail later on, but something is hanging above the ground and you drop it, that means it can fall. And so that, if it's hanging up here, it has potential energy. So things like the streetlights or the flag, they have potential energy. So what about in here? In this class, what would you say is related to chemistry? Everything. Why everything?
Everything is either matter or energy.
Everything's matter or energy, and chemistry is the study of matter and energy. So everything is related to chemistry. And so, 5 weeks from now, when you're hitting yourself on the forehead saying, why do I need to know this stuff? Because everything is chemistry, that's why. Say it to yourself. It won't work, but it might. If you wanted to categorize things in here, how would you categorize? You can make your own categories. You can be as creative as you want.
Potential.
There's potential energy and matter. So we've got the matter and energy, right? All the things are matter. The light is energy. There's kinetic energy. So we've got the matter and energy. Let's just focus on the things that are matter. How can you classify the things that are matter?
Living and non-living.
Living and non-living.
Solid liquid gas.
Solid liquid gas.
Heavy light.
Heavy and light. Brown and gray. Light and dark. Right? You can make all kinds of different classifications. That's what today's lecture is mostly going to be. Classifications. Okay? We have to figure out where in this pyramid of chemistry everything fits. Because we had chemistry with matter and energy, but that's going to become a whole lot more things. Okay? So, we have matter. The first set of classifications, we can break them up into pure substances and mixtures. What do you think is the difference between a pure substance and a mixture?
You can separate a mixture.
A mixture you can separate. If you can separate it, what does that mean about what it's made out of?
More than one substance.
A mixture is more than one thing mixed together. A pure substance is one thing. So give me an example of a pure substance.
Gold bars.
A gold bar. Water. Those are pure substances. What's an example of a mixture?
Sodium chloride.
Sodium chloride.
Dehydrated.
Say it again.
Sorry, dextrose water.
Dextrose water. Wow.
Dehydrated.
Yes. Yes.
Sorry.
It's glucose. So it's something that you would give a patient in nursing.
Fine.
Pretty much most things around us are mixtures. The plastic, that's a mixture. Paper, it's a mixture. Air, there's multiple gases in the air, so that's a mixture. So we're going to break those down further. We're going to start with the pure substances. Pure substances we can break into elements and compounds. This is probably the easiest one. How do you think you can tell if something is an element or a compound? And keep in mind, it's really, really easy, especially when you're sitting in this class.
An element has one type of atom and the compound
It has one type of an atom. Compound has more than one type. How do you know if there's more than one type of atom?
Capital letter.
Say it again.
the
Like
number of-
on an atom starts with a capital letter.
the
Okay.
number of protons.
Number of protons. You're correct. There's an even easier answer. She's looking at it. If it is here, it's an element. If it's not there, it's not an element. Okay? And so when we write chemical formulas up here, if what I write is up here, it's an element. What I write is not up there, it's an element. It's not an element, so it'll be a compound. So I write Zn, that's zinc. Zn is right there. It's an element. If I write That's methanol. Is that up there? No. The C is up there, that's carbon. Hydrogen is up there. Oxygen is up there. But as a whole, that's not up there. So that's a compound. It's made up of more than one element. So what is an element? What makes something element so that it gets on the periodic table? It is a substance, and when we say a substance, we mean something you can hold. It's a type of material that you can't break it down any further. Okay? If you take sodium chloride, you can break that into sodium and chloride. But if you take sodium, you can't break it down any further. The elements up here are basically building blocks. Well, they're like Legos. You can take all the different Legos, put them together to make something big. But once you take it apart, Legos are really, really hard. If you ever stepped on one, you know that, right? You're not going to take that Lego apart by your hands, right? So an element is like the most basic building block, okay? We have all those different building blocks. Once you get down to just one block, you can't go any further, even if you use a chemical reaction. So those are all of the known elements. These are all the new ones. Most of them don't even have official names yet. They've existed for a nanosecond in a lab somewhere, and so they go on the periodic table. But most of the ones we're going to be dealing with are up at the top. So this is the periodic table. Over the next few weeks, we'll learn how to really read that table. There is a lot of information in that table that you don't know about. Even things that aren't actually written there, you can get from it, just by looking at where an element is. Okay? So that's arsenic. I can look at that, and just based on where it is on the periodic table, I can tell you how reactive it is, how many electrons it has, how many shells of electrons it has, what it's like, generally how big it is, things like that. And that's not even looking at the numbers that are up. Yes?
So is that something that we're going to have to remember?
Not the whole thing. There's a slide coming. Maybe, okay, not yet. So, we said pure substances, we have elements and compounds. Elements we can break down even further. Elements, there are nonmetals, and there are metals. And this is also easy, okay? You can do it, and you don't even know how you're doing it yet. That's phosphorus. It's the yellow stuff here. Would you say that's a metal or non-metal? Just look at it.
Non-metal.
Say non-metal. What about copper? Metal. Bromine is the liquid in there. Non-metal. Nickel? Lead? Gold? Carbon? Non-metal. Aluminum? Sulfur? Tin? You got them all right. How'd you know? What about looking at them? I heard it. Shiny. Yes, that is the technical term we are going to use. Metals are shiny. Okay? Not only are they shiny, they conduct electricity. You can't tell that by looking up there, right? But if you want to run a wire, well, what's a wire made out of? Metal. If a power line falls down, what do you not want to touch that's touching the power line? Metal, right? Think about things that insulate you from the electricity. Are they metal? No. So metals are shiny and they conduct electricity. That's magnesium. That's kind of shiny. It's not a solid block of metal like you're used to, but it's shiny, right? That's selenium. That just looks like a rock. That's not shiny. Selenium is not a metal. If it's not a metal, it's a non-metal. So the definition of a non-metal is something that's not a metal. It's dull, it's not shiny, and it doesn't conduct electricity. So ask yourself, is it shiny and does it conduct electricity? If the answer to both is yes, it's a metal. If you have a no, it's a non-metal. Okay? They don't know what they are. They're just not metals. So, we went through and we labeled these, right? So do you remember what phosphorus was? Non-metal. Phosphorus is here. You know gold's a metal. Gold is there. Carbon was a non-metal. It's there. Copper is a metal. It's there. Bromine is a non-metal. Aluminum, there. That's a metal. Sulfur is a non-metal. Nickel is a metal. Lead is a metal. And tin is a metal. Did you see a pattern? What's the pattern?
Left side of metals.
The left side is metals. The right side is non-metals. Okay? Most periodic tables, and if I remember to bring a marker next week, ours will also. But most periodic tables have a dark line drawn like that. It's a stair step. Everything to the left of that stair step is a metal. Everything to the right of that stair step is a non-metal. So you can tell by looking at it, is it shiny? Yeah. It's a metal. Or if you don't know what it looks like, if I ask you, what is zirconium? What is it? Metal or non-metal? Metal, because it's on the left. That's another thing that the periodic table tells us. It will tell us whether it is a metal or a non-metal. So we can get smaller and smaller. So now we're down to atoms. Matter, anything that is matter, is made up of atoms. Atoms are these building blocks. The elements come in atoms. So an atom is the smallest piece of an element that you can break it down into, and it stays that element. Okay? So I said an element is the smallest thing you can break something down into, and left it at that. But atoms actually do have what we call subatomic particles. Okay? That's a later lecture. But an atom is the smallest unit of an element that has all of the parts needed. Every element has a symbol. It's either one letter or two letters. Okay? Carbon is capital C. Calcium is Ca. It can't be capital C because carbon's already capital C. And so carbon's more important than calcium, so carbon gets just the C and calcium has to have the A. Okay? A lot of them make sense. Like that's titanium, Ti. That makes sense. But iron is Fe. You see that and you want to say Fu, but why is iron Fe? Iron, shouldn't it be IR? There's no IR up there. Why can't it be IR?
It was old terminology.
Old terminology, how old?
Like really old.
Like really old. Okay?
Where's the IR located?
Iron is there.
Right, but what's
Down.
77?
Oh, there is an IR. That's iridium. Yes. But iridium is much less common than iron. So you would think iron would be IR. But do you know what the Latin word is? Ferrum. And so in a lot of in the old chemistry books, even 100 years ago, even in English, iron is called ferrous. And when we talk about compounds that have iron in it, you can use the words ferrous and ferric. Okay? We're not going to use those, but that is where the Fe comes from. So these are some of the weird ones. So copper was cuprum, things like that. Okay? Lead is always plumbum. Other than these, most of them make sense. So, getting back to your question, these are the ones you need to memorize. Okay? They're in the lecture notes. There's also in Canvas, down by the syllabus, there's a file that just has this, okay? I blacked out the ones that you don't need to know. The other ones, you need to be able to go between the symbol and the name. So if I give you Mg, you need to tell me magnesium. If I ask you what's the symbol for cobalt, you need to be able to tell me CO. Okay? You need to know this for next week's quiz. After next week's quiz, you don't have to have this memorized at all. Okay? After next week's quiz, you will have a periodic table for everything after that.
Even the final?
Even the final. Okay? So, you're thinking, why am I making you learn this if you're going to have a periodic table?
A lot of formulas.
A lot of formulas, and so since we have so many formulas, if you have to look it up every time, you're going to spend the entire semester looking up what potassium is. Okay? And if you have to look up what potassium is every time, you're not going to be learning the hard stuff. And so if you memorize it now, the rest of the semester, you'll at least have something to fall back on. Okay? By the end of the semester, by halfway through, the important ones, you'll use them so many times that you'll memorize them anyways. But this gives you a good head start, and it gives you an easy way to get some quiz questions right. Because if you memorize them, you're good. Okay? So not all compounds or substances are just atoms. If you take multiple atoms, put them together, you have a molecule. And it doesn't matter whether you take two of the same type of atom, or if you have three atoms, two of them the same, one of them different, put them together, it's still a molecule. That's a molecule, and that's a molecule. A molecule is just a unit of atoms that are stuck together. And this is discrete arrangement. What that means is that it doesn't change. And so here, the black one is in the middle and you get two red ones. That means it's always going to be like that. You're not all of a sudden going to have two red ones and a black one. That molecule is a black one with two red ones. Like we said, they can be same element or different elements. So that's our pure substances. It's a good time for a break. Let's take a break. We'll start at 7:30. My watch, man. Yes, 7:30. We'll start again. Probably incognito window, I'm just doing it again. Because if you use the incognito window, it typically has no cache whatsoever. Even if you clear this, it uses something. That's good. You were able to do that one? So you're doing a piece of paper, you can scan it or take a picture with your phone, and then there's an upload button. You can upload it. If you don't have a way to do it or don't want to do that, you just do it with a piece of paper. Make sense? Where are you going?
Going into a I keep sliding out. So, thank you. I just need to exchange it with someone else. Thank you. Hopefully this doesn't slide. Oh, this is much better.
I'm going to pass you a little piece of paper out. This is contact information for a tutor. Okay. The department has their own tutoring office here. It's in, I don't really know where it is. With the computer lab in this building, it's attached to there. Okay. So there's contact information for the woman here. You can just email her or call her and set it up. They also do tutoring in the HA building. I don't know what the HA building is, but they do chemistry tutoring there also.
There's no way to, you're gonna miss. And so what you have to do is you have to plan to do that makeup lab, and hopefully you won't miss anything. So if you do that makeup lab and you don't miss any more, everything will be just fine. You won't lose anything whatsoever. Say it again? Where?
But I can do the makeup lab.
If you do the makeup lab, you get full credit for that when you miss. And if you don't miss any more, it's like you were there for all. This little booklet up here kind of shows you the things that they'll go through you with at that tutoring office. I think they do this kind of, they not only do chemistry tutoring, but also general tutoring, how to be a better student, study skills type thing. So just some example stuff in here. But they do specifically tutor for this class. In this office, they are, the chemistry tutors are CHM1030 tutors. And in the HA building, they are chemistry students from UF that come and tutor whatever chemistry students from Santa Fe come to. And students in the past have had better luck with the tutors here because they're specific for 1030, and it's over in the HA building, they get a lot of students and a few tutors. So there's one tutor trying to do 5 students, and they're in 3 different classes. And it just, from what I heard, it doesn't work this way.
So you post the lecture slides after each Tuesday session?
Before.
Before.
Before. So if it gets to be a day before and I haven't posted them, someone remind me. Okay. I have them all saved as PDFs. I just don't post them all immediately because when professors post slides, you print them and then we change them. You don't like that. And so I don't post them until I know they're my final slides. Work. Everybody back. Everybody see somebody that's missing? You think she left? She left. So if we breaks that down, if we start 3 minutes early, we finish 3 minutes early. Sound good?
Do it.
So if she does come back, I will apologize, and I will tell her what she missed.
That's nice.
Working? So that's this. We talked about this side. This side is pretty easy. Okay. Over here is going to get a little hairy. A compound is made up of 2 or more different elements, and they have to be in what we call definite proportions. So that means if you have H2O, how many hydrogens do you think are in H2O? There are 2. Okay. How many oxygens are in H2O? 1. So we have H2O. That 2 means there's 2 of those, and there's an assumed 1 there. We don't write the 1. So if there's no number, that means there's a 1. So that means in water there are 2 hydrogens for every 1 oxygen. So if I have H2O2, that's not water. That is a different compound. That's hydrogen peroxide. And so if you change the proportions, you change the chemical formula. If you change the chemical formula, you do not have the same compound anymore. And they, not only that, but they have to be bound together. So this is iron pyrite, Fe2S3. It looks like that. If we take some iron and some sulfur and mix them together, we get that. That is not that. That is iron and sulfur mixed together. That is iron and sulfur bonded together in a molecule. Okay? So here, you can't separate the iron and sulfur from each other. You'd have to just have a chemical reaction to get them apart. Over here, you can just put a magnet over it and it pulls the iron out. If you wanted to, if you were really bored, you could go through and put the sulfur over here and the iron over there. But you couldn't do that for here because they're bonded together. When you take the 2 elements and put them together to make a compound, that compound is going to be very different than the 2 elements that went into it. So this is sulfur, that's iron, but that is iron and sulfur in a compound. They look nothing alike, do they? It's a completely new thing. You know what water is like. What's hydrogen like? Hydrogen is a gas at room temperature. So is oxygen. But you put them together, and you got water. And so they're nothing alike. So water is our compound. You can actually break water apart. It's called electrolysis. All you have to do is pass some electricity through water, and it actually breaks apart into hydrogen gas and oxygen gas. Okay? Now here's a tricky question. One of these, so you pass electricity through the water and you get bubbles. One of these is collecting oxygen, and one of them is collecting hydrogen. Which one's which? How can you tell? I mean, they're just empty tubes. What about the hydrogen being two? There's twice as much, twice as many hydrogens, right? So how can you tell which one's hydrogen? The one that has the most. You get twice as much hydrogen gas as you do oxygen gas when you break water apart. That one has twice as much as that one. So when you break apart a compound, you get elements. You get hydrogen and oxygen. Sand is a compound. It's silicon dioxide. Okay? What does that formula tell us about the ratio of elements in silicon dioxide? It means there's one silicon. Remember, there is an assumed one here, and two oxygens. So for every one silicon, there are two oxygens. Look at that. Is that an element or is that a compound? Element. How do you know?
Lowercase e, not capitalized.
Yes, yes. So you know that lowercase e goes with that h, right? So once you know that e goes with that h, how do you know it's an element, not a compound? It's not more than one element put together. And how do you know it's not more than one element put together?
Because we don't have all the numbers and
Right. There's the easy answer. He is number 2. It's right there. That's an element. If it's an element, it's not a compound. H2O, element or compound? Compound. Sodium chloride. Why? Sodium, which is up there, and it's chlorine, which is up there. Put them together, the compound. Copper. Element. It's right there. Now we get into mixtures. And so when we had that picture of the iron pyrite and the iron and sulfur together, the iron pyrite was a compound, the mixture was a mixture. You just took two things and mixed them together. The difference between a mixture and a compound is that you can separate a mixture just by what we call a physical process. Like I said, you can put a magnet over it. You can, molecule by molecule, separate them apart. You can just move them apart. You can't move apart the atoms that are in a compound. So pencil lead is a mixture. Salt water is a mixture. You have salt. You have water. Air is a mixture. There's oxygen, carbon dioxide, argon, methane, CO2, and anything you want. There's all kinds of gases in the air. That is a mixture. But you can separate the things that are in those mixtures from each other. So this is how they get salt. They take ocean water, salt water, and they let it evaporate. The water evaporates, salt's left behind. That was not a chemical reaction. You just separated the two because the water evaporated and went away. So you can separate the two in the mixture. We're going to break the mixtures down into different types of mixtures. Okay? There is homogeneous mixtures, and there are heterogeneous mixtures. The definitions are nice and clean, but when you start to use them, some examples can get kind of questionable, and we'll see them. So a homogeneous mixture is the same throughout. If I have a glass of salt water, it's the same at the top as it is at the bottom, right? A heterogeneous mixture is not the same throughout. If I have a thing of pond water, and I set it here, and I wait 5 minutes, what's going to happen? It's going to settle out. The mud and the silt and things from the water is going to settle out. You're then going to have silt and mud at the bottom, and cleaner water at the top. It's not the same throughout. So we call that heterogeneous. Homo for one, hetero for more than one. So let's figure out what these are. Salt water. Homogeneous or heterogeneous?
Homogeneous, because it's the same throughout. Lake water. Heterogeneous, because we said there's mud in there. Not only will it separate out, but there may be floaties in there. There's never going to be a floaty in a homogeneous mixture. Because if you have a floaty, that means you have floaty and you have water. And that's heterogeneous. Tap water. Depends on where you live, probably. Hopefully your tap water is homogeneous. Hopefully there's no chunks coming through your faucet. But if there is, that would be heterogeneous. Okay. And about air? More or less, it's more or less a homogeneous mixture. I mean, the air up here is no different than the air back there. But, yeah, so imagine I release a colored gas up here, right? At that point, there's colored gas up here, there's no colored gas back there. But if I give it enough time, what's going to happen? It's going to spread out, and then it will be homogeneous. And so a heterogeneous air is just a point in time. It hasn't gotten to the point that it's completely mixed yet. Okay. What about brass? It says it's an alloy of copper and zinc. Can you picture what brass looks like? It's homogeneous, right? Can you think of a time that brass would be heterogeneous? You may only be able to come up with this if you actually have something that's brass.
Melted?
No. It corrodes. Rusting isn't the right term, but that's beyond this class. It corrodes. It reacts with oxygen in the air, and it gets this nasty blue-green stuff on it. Okay? Then it's heterogeneous, because you have nasty blue-green crap on the outside, and you have nice brass in the middle. And so, if you saw that as a quiz question, and I don't say it has nasty blue crap on the outside, assume it's homogeneous. Okay. What about potting soil? Say homogeneous? So heterogeneous. Potting soil is probably heterogeneous. I mean, there are leaves and the little perlite, little white things in there, you know, worms and stuff. It's not very homogeneous. What about chocolate chip cookie dough?
Oh, no. No, wait, because there's different amounts of chocolate chips.
This is the one everybody argues about.
It's heterogeneous.
The obvious answer is heterogeneous. But you can make a case for homogeneous. I mean, I had somebody say, it's a chocolate chip cookie dough. Chocolate chips aren't dough, which means you're only talking about the dough, not the chocolate chips.
Gotta get all technical.
And so, hopefully, what you see is the obvious answer here is heterogeneous. You have dough and you have chocolate chips, and even if you look at them together, there's probably more chocolate chips on one side than the other. If you counted them, there's probably 50 on one side and 52 on the other. Okay? It's heterogeneous. But if you're ever giving me an answer, and you say, well, it depends, tell me how it depends. Okay? If I am looking for heterogeneous, but you say homogeneous because this is only looking at the dough, I'd say, okay, you stretched that a little bit, but I'll give it to you. Okay? If your thought process is correct, you will get it correct. But if you go off in the left field and don't explain how you got into left field, I'm going to assume you were trying to hit it the right field and you ended up in left field. Okay? So if you question, tell me. Worst case is I still mark it wrong, but I probably will mark it right if your thought process is right.
I'm still stuck on the brass because it's made of copper and zinc.
It's copper and zinc, but they're mixed equally.
Okay.
Let me see if I can find a picture.
Didn't you say like one was there?
See, there's an asterisk that says depends on presence or absence of suspended solids. And so if you wanted to be careful with answering that question, you could say, if there's floaties, it's heterogeneous. If there's no floaties, be homogeneous. So that's brass. And so you can see it's the same throughout, right? But if we put corroded brass,
Oh,
that's heterogeneous, right?
is it because now you have two substances?
Yes.
The
Yes.
corrosion and the brass itself?
Correct. The,
Okay.
the brass on the outside reacted with the air to make a different thing. That is no longer brass.
So if you can't see a separation, it's always homogeneous.
If you look at it and it's the same throughout, it's homogeneous. So what about Gatorade? Homogeneous, heterogeneous? Homogeneous. Coke. Coke's always the tricky one. Think about it. Homogeneous, but
That's carbonation.
has carbonation. So before you open it, it's homogeneous. When you open it, there's bubbles. It's heterogeneous. If you let it sit there a while, the bubbles go away. It's homogeneous. And so if the question asks you, is cola homogeneous or heterogeneous, you might want to tell me which situation you're looking at. Okay? So this is our big flowchart. I'm not going to go through it again. We covered everything in there, but if that helps you, that's great. We talk about matter in a number of different ways. We talk about it at different levels. The first level is the macroscopic level. Macro means big. The macroscopic level of matter is what we can see. You can describe this desk as how you see it. That is the macroscopic matter. Then there's the molecular level. You can't see it, even with a microscope, but you can draw it. You can draw what the molecules look like. You can draw what different molecules look like and what they're doing. That's the molecular level. And then there's the symbolic representation, which is this. It's this. So, where's the marker? Okay, 3 of them over here. So that is the symbolic representation, but I can draw an oxygen with 2 hydrogens. That'd be the molecular level representation. It's just a drawing. That is the symbols. So this is the molecular level representation of copper. Copper is an element. If you have a chunk of copper, it's just a whole bunch of copper atoms lined up. This is helium. Helium is a gas. In a gas, we'll talk about this more later on, but in a gas, the atoms and molecules are further apart. So there's a lot more space, and not only that, you have this little marking here, which is the international symbol for movement, right? You draw little speed lines, a little shadow, and you automatically know there's moving. Here, there were no little speed lines, there's no shadows, it's not moving. In the solid, they just sit there. In the gas, they fly around. Is this atoms or molecules? Molecules. Somebody say atoms? Could you say atom?
Yeah.
Yeah. Why? Because the molecules are made of atoms. And so these are molecules, but these are atoms. Is it an element, a compound, or a mixture?
Compound.
Why is it a compound? There are 2, but what you're going to have to make an assumption. The fact that they all look the same, what would you assume that means?
It's the same element.
It means you have to assume it's the same element. And so it is a molecule, but you can have an element in molecule form, which is what this is. Even though it's a molecule, because everything in that molecule is the same element, it is an element. The compound has to have more than one type of element. and this has only one type element, and it's not a mixture because all four of them are the same. If there was a fifth black one down here, that would be a mixture. Because they're all the same, it's just an element. So, element, compound, or mixture?
Compound.
Why? Why a compound?
More than one element combined.
When you look at them individually, you have two different elements together, but all four of them are the same, so it's a compound. What about this one? Element. That one? Mixture, because you have blue atoms and you have black atoms. How about this one? Mixture. You have this molecule and those atoms. What about that? Mixture. You have two different types of molecules. So a mixture can be two different elements. You can have compounds and an element. You can have two different compounds. If you have more than one different thing, doesn't matter whether it's an element or a compound, if they're mixed together, it is a mixture. So gotta talk about states of matter. You know these. What are they? Solid, liquid, gas. Boom. Moving on, right? What are the macroscopic properties of solids, liquids, and gases? If you were going, macroscopic is real world, right? How would you describe a solid in the real world?
You can see it.
You can see it. Is it tangible? It's tangible.
Tightly packed down.
That's not macroscopic. We'll get there. What else? It's hard, right? It's solid. Solids are solid. Right? Is this table, when we come in next week, is it going to look different? No. It's not going to change shape. It's not going to change size, right? Unless somebody karate kicks it, then it might change shape. Please don't karate kick it. What about the macroscopic properties of a liquid? The fluid. What do you mean by fluid?
Moves.
It moves. Moves in what way? It's different shapes. It conforms. It takes the shape of the container, right? So his Coke in that bottle up there takes the shape of the bottom of his Coke bottle. If he poured that out into a glass, it would take the shape of his glass. Is that liquid going to change volume? No, not easily. What about gases? How would you describe gases in a macroscopic sense? You can't really see them. The volume, how and when does the volume change? What can you do to change the volume of a gas? Heat it or cool it, right? So you can easily change the volume of a gas a lot. We'll have a whole lecture on that. But you know that. If you heat a balloon, it's going to expand, right? What about the shape of a gas? It takes the shape of the container, just like a liquid. So a solid has a definite shape and a definite volume. Liquid has a definite volume, but no definite shape. And a gas has no definite shape and no definite volume. Now, let's get to the molecular level. She said in a solid, the atoms are closely packed. That is true. How much are they moving in a solid? They're not moving at all. They kind of vibrate. They just kind of sit in place and shiver. Okay? What about a liquid? What do you think a liquid looks like at the molecular level?
They might look like a solid, but they move.
They're close together, but they move. Okay? They're a little bit further apart than the solid, but not much further apart. They're just enough apart that they can move past each other. So if you have water, all the water molecules in that are moving around each other. That's why if you pour the water into a different shape, it can change its own shape because the water molecules can move. But if you put an ice cube in a round glass, the square ice cube doesn't become round because the atoms aren't moving. Okay? And what about a gas?
Very fluid.
They're moving around a lot, they're moving around very quickly, and they're a long ways apart. Okay? When you melt something, you take it from a solid to a liquid, it gets just a tiny bit bigger. There are actually exceptions. Water is an exception. When you melt an ice cube, it actually gets smaller. Right? When you freeze water, it expands. That's why you don't put a water bottle in the freezer, or if you do, hopefully you remember it before it blows up. Because it expands until the bottle blows up. These are what we just talked about. They're properties of the states that you already know. You know these things.
What's plasma? Is that word?
Plasma is, it's kind of in between a liquid and gas. It is its own state of matter. We're not going to talk about it because it's well beyond this class, it's well beyond anything I've taken. And actually, a year or so ago, they discovered a fourth state of matter, which is called the Jahn state of matter. Yes, but it wasn't me. And I don't know the guy. The guy's long dead.
Oh.
But it's got my name in it, right? There's 4 states of matter. My name is in one of them. There's no solids in here, right? There's no Mr. or Mrs. Solid or gas, right? But there's a Jahn state of matter. We can talk about that. Gases not only can be expanded by heating, but you can compress them, right? You can just push them, and they're going to compress. If you push on a liquid or push on a solid, you might pull something, but you're not going to compress it. By gases, you can just pump it in there, it's going to get more and more compressed. Pressure's going to go up, but you can keep doing it as long as you want. States of matter are not set in stone, right? We can go between them. Here we have a glass of water, and it's evaporating. The water in the glass is evaporating. It's going from a liquid to a gas. It's also condensing. The condensation is going from a gas to a liquid. And so this happens all the time. You put a cold glass of water on the table, it evaporates, but also because it's cold, the humidity in the air will condense on the cold glass. So we have 2 changes in states of matter going on here. We have evaporation and condensation. We have symbols that we use for different states of matter. These are simple ones. Solid is an S, liquid, L, gas, G, and then aqueous. Aqueous means dissolved in water. We'll come back to this one. But that's aqueous is AQ. And you just put it right after the chemical formula. So this means bromine solid, bromine liquid, bromine gas, and bromine dissolved in water. So sodium chloride, which is salt that you put on your food, is NaCl with an S. What does that describe? What is that telling me that I have if I have NaCl with an S? It's a solid. A solid of what? It's a compound. What does it look like on the macroscopic scale? Little white grains of salt, right? What does it look like on the molecular scale? Say it again? Because it's a solid, they're sitting there vibrating, yes? It's an atom of sodium and an atom of chlorine bound together, vibrating, and they're very close together because it's a solid. So that's the molecular level. Next thing we have to talk about, physical and chemical changes and physical and chemical properties. A physical property is something that we can observe about an object or a substance or matter without changing what it is.
I can observe this desk. I can look at it, I can hit it, I can pick it up, see how heavy it is, and I don't change what it is, right? That is a physical property. Color, smell, weight, density, things like that are all physical properties. I can just measure them. That's all I have to do is just measure it. Color and odor, mass, volume, density, temperature. Mass is how much something weighs. Volume is how much space it takes up. Temperature is how hot it is. These are qualitative properties. Qualitative means you can't put numbers to them. You can't put numbers to what something smells like. And unless you know HTML, you can't put numbers to color. Any coders in here?
I was about to ask you.
Okay. So if you do HTML, every color has a number that goes with it, tells the screen what color to show. But that's computer science, not chemistry. So you can't put a color, you can't put a number to color. You can't say blue is 17, right? But you can say something weighs 5 pounds. Something is 6 liters. You can measure that. You can't measure what something smells like. So quantitative, quantity, meaning numbers. So a physical change is a change in a physical property. So if the color changes, if what it smells like changes, if the mass changes, if the volume changes, if any of these things change, that is a physical change. So the physical properties change, but what it is, its chemical composition did not change. If I did karate kick this desk, it's now in 2 pieces. It's in 1 piece now. The physical properties changed. But what it's made out of didn't change. I just now have 2 pieces. And so that's not a chemical change. If you change the state, if you boil something, it goes from a liquid to a gas. If you freeze something, liquid to a solid, or any of those changes, that is a physical change. Because it is still H2O. Ice is H2O solid. Water is H2O liquid, and then you have water vapor, H2O gas. It is still H2O. And so when you change physical state, that is a physical change. That is a very common quiz exam, final exam question that people will mess up over and over and over again throughout the semester. It's not hard, you just have to remember. Okay? So what is this? This is evaporation. We have liquid water, molecules are close together, going to H2O gas. Is that a physical change?
Yes.
Yes. It is still H2O. Okay? These arrows, we're going to use these over and over again. That means you read it as the word yields. This yields that, but it really means goes to that. This turns into that. This turns into that. Just follow the arrow. It means things are going that way. Yes, we can go between solids and liquids. We can go from liquids to gases in both directions. But we can actually go directly from a solid to a gas. You ever seen dry ice? It sublimates. This is sublimation. It's carbon dioxide solid going directly to carbon dioxide gas. It is not going solid to liquid to gas like water would. It goes straight from solid to gas. So here is a drawing of CO2 solid. If you wanted to draw CO2 gas, how would you draw that? What would it look like at the molecular level?
A compound of carbon.
They're moving, right? And so you're going to have a CO2 molecule. It's hard to see here, but a CO2 is a black and 2 reds. You'd have a black and 2 reds here, and a black and 2 reds, and a black and 2 reds. And you put the little lines behind it, telling you this. Okay? So it goes from close packed together to far apart and moving.
So that's what it would look like. We can go the opposite direction. So CO2 sublimating is something that you see in real life. You don't see sublimation all that often, but my guess is the majority of you have seen dry ice before. But you can go straight from a gas to a solid, and that is called deposition. I remember it as you're essentially depositing things on a surface. We'll do this in lab, okay? We'll take iodine. Iodine at room temperature is just a chunk. It's a solid. We'll heat it up. It will go straight from a solid to a gas. We'll get purple gas coming off of the iodine chunk. And then that purple gas will deposit on a cold surface, and you'll get purple crystals forming on the cold surface. And so we'll go from here to here and back. And so there are these 6 state changes that you need to know. You need to know the name of them and what they are. But you already know most of them. You know melting and freezing. You know condensation, that's what's on the outside of your cold glass of water. This calls it vaporization, but it's evaporation. You can call it evaporation. I will call it evaporation. Okay? You know evaporation. And so you've essentially got 4 of them down. You just got to focus on the other 2. Okay? But all 6 of them are fair game. It shouldn't be too hard. Okay. So those are physical changes. They're changes in physical properties. A chemical change is a change where what you start with chemically, the formula, is not the same as what you end with. And so a chemical change is when we broke H2O into hydrogen and oxygen. Because we started with water and we ended up with hydrogen and oxygen. It is not the same thing. And so a chemical change, another word, and what we'll call them, chemical reactions. So if you look at something and you say, that's a chemical reaction, that's a chemical change. Boiling water, even though you don't really know what a chemical reaction is yet, you could probably tell me boiling water is not a chemical reaction. And so if it's not a chemical reaction, it's a physical change. If it's a chemical reaction, it is a chemical change. So you take substances, one or more, and you change what they are. So if you were going to write the formulas out, what you wrote at the end would be different. It's going to change. If you have a new penny, what does a new penny look like?
Shiny.
Shiny. What does an old penny look like?
Brown.
It's brown, right? It's not shiny. So, a penny, when it starts out, is copper. Just copper. Afterwards, after a long time, it tarnishes. It reacts with the oxygen in the air, and you get copper oxide. And so, you started with copper, and you end up copper oxide, copper with oxygen. Is that the same as what you started with? No. So that is a chemical reaction, that is a chemical change. When you burn gasoline, you start with gasoline, you end up with global warming, right? That is not the same thing. But clearly, when you burn gas, you get carbon dioxide, you get oxygen, you get all kinds of different gases, you get water, you get a lot of different things. But what comes out of your tailpipe is not gasoline, hopefully. If it is, you're probably not going to make it to lab on Thursday. But clearly, it is not what it started as. That's a chemical reaction, a chemical change. Good. Not only can you take water and split it apart into hydrogen and oxygen, but imagine we have those tubes there. We split it up. If we took them, mixed them, and gave it fire, we'd get water. So we can take hydrogen and oxygen, and put them back together to get water. That is a chemical reaction. It's a chemical change. It's also a chemical change when we split them apart. So here we have oxygen and hydrogen. We give it fire, and we get water. So this is definitely not the same as that. We can tell on multiple levels. Here, the red and the white are separate. Here they're together. If we look at just the formulas, we have H2, O2, and H2O. What's on the right, what we ended up with, is not the same as what we started with. So that's a chemical change. There are three things that you look for as evidence of a chemical change. If something bubbles, that's a good hint of a chemical change. The obvious exception is if you're boiling something. Because we said boiling is a physical change. If you boil it, it's going to bubble. But if I take baking soda and vinegar, and I put them together, what happens? It foams up, it bubbles. But I'm not boiling it, I just mixed them. That's all I did. And it bubbled. So that's a sign of a chemical reaction. You also have a permanent color change is a sign of a chemical change. And so if I start with, well, our brass. We had our brass as kind of a shiny gold color. When it tarnishes, it turns blue, blue-green. That is a sign of a chemical change. Because you can't take that blue-green stuff and put it back in the brass. But if you took metal, let's say steel. What color is steel?
Silver.
Silver colored. If you get it really hot, what color is it? Red. What happens if you cool it back down? Goes back to silver. So that's not a permanent color change, right? Because you can easily put it right back. You just have to undo what you did. But you can't just undo a chemical reaction. So that makes it a permanent color change. Or if you have a sudden change in temperature, that's a sign of a chemical reaction. You ever use the instant hot packs? That's a sudden change in temperature, right? There are two chemicals in that pack that are separated from each other. You normally have to break a little packet that's inside. You mix the two, and all of a sudden it gets hot. The same thing with the instant cold packs. You mix the two chemicals, and it gets cold. That's a sudden temperature change. That means there's a chemical reaction happening. If the temperature changes on its own, it has to be a chemical reaction. Here's boiling water. Physical or chemical change? Physical. It's a state change. Remember, state changes are physical changes. Is this physical change or chemical change? Chemical. We have oxygen and CH4, which is methane. So this is burning methane. Methane burning with oxygen to give us water and carbon dioxide. What we ended with is different than what we started with. What's this? Physical. This is our carbon dioxide sublimating. We have CO2 molecules in the solid form and CO2 molecules in the gas form. It is still CO2, so it's not a chemical change, so it has to be a physical change. Okay. This.
Are all mixtures chemical change?
Making a mixture. So imagine we had the sulfur, we had the iron in that picture. If you had sulfur over here and iron over here, and you mix them together, I would call that a physical change. And if you took the sulfur and you separated them back out with the magnet, that would be another physical change. Because even though after you mix them, you have sulfur and you have iron. They're just next to each other. If they reacted together to make the iron pyrite, that would be a chemical change. Because now you have iron pyrite. The iron and the sulfur are bonded together. So that would be a chemical change.
So some of them can be either or. Pretty much.
If it's a mixture, making or separating a mixture will be a physical change. If you make or destroy a compound, that would be a chemical change.
So we got another one of these phone things. And we're going to do this, well, we're going to do this multiple times. And so first we're going to do it individually. I need to make it active though. So if somebody just sent it in, I just deleted yours. We'll forget to do it again. So before you send it in, let me tell you what you're looking at. Okay. So this is it's a coffee filter, and it's folded up in half and then in half again to make a kind of a triangle shape, if you can picture that. And then black Sharpie was used to color the very tip, and then it was set in a glass so that just the tip was in the water, and the water, because the coffee filter, soaked up through the filter, and when you were done, took it out, and you had that. Do you think that is a chemical change or a physical change? If you think it's chemical, text 128352 to that number. If you think it's physical, text that number to the same number. Anybody still working? Let's see what we got. How many? Let's say it's 61% chemical, 39% physical. So somebody who said chemical wants to defend why it is chemical.
Color change. Permanent color.
Permanent color change, is that what you're going to say? Anybody have another reason to say chemical? Okay. Somebody who said physical, do you want to defend why it's physical?
Because black is essentially every color mixed together. So Sharpie, if the colors would separate, they could separate out and it wouldn't be chemical. If that makes sense.
Okay.
That's how I put it. As the water comes up, you said they dip it in water, right?
Correct.
So the water might push some of the colors out away from each other, so then they would become separate again. But I don't think that's chemical.
It's both.
It's not both.
I mean, chemical isn't it what you started with is not what you come out with, right?
Right.
So.
And so I'm essentially asking you, are you ending with what you started with?
No.
And
So-
I don't think it's also not permanent because you can mix another color with one of those, I guess.
Or you could like bleach it.
So,
Is that like a different?
so what we're going to do is we are going to get into groups, and I'll make groups, and you're going to try to convince the other people in your group that what you said is correct, okay? And after we discuss it, we're going to break back out of the group, and then you're going to vote what you think. So if you think you're right and everyone else in your group is wrong, you still vote what you think, okay? And so what we'll do is we will have, if you 3, you 4, you 4, you 4, look at this, you 3 back there, and you can join that. So try to convince your group members that you are correct.
Well, for both of you,
You say chemical. Because that color, you're not gonna change it to, unless you do another mixture, and take another color.
I feel like it's physical because, I mean, yeah, you're not really like starting with the same picture that like you began with, you know, like it was a black tip and there was no color. But I feel like mixing it with water didn't really change the chemical composition of like either the water or the actual filter. Like, yeah, it basically changed the color. I don't think it changed the actual composition of either the coffee filter or water. I don't know. I was thinking in my head, and it sounded better in my head, but I don't know how to explain it very well.
You're doing that
Yeah.
When it was after the whole thing, right?
Like when you think about it, like with common sense, it feels like a few days ago. Like it's not like kind of, I don't know. It doesn't seem like a big change. Yeah, but how does it? The details is saying it's expensive.
I just feel like they were two things that were put together and stuff like that. You know what I mean?
Yeah.
Or you could bleach it, take the filter.
Right. I don't know.
Well, I don't think we can take that and make it black.
No, unless you combine other.
Yeah, unless you have something
Right,
like
and then
combining
something else together.
Can we vote again now?
You done arguing? Anybody still arguing? Okay. So, what you can do, go back on your own and send in your answer again. No one changed your mind? Say the same thing. Yes?
What if your phone's dead?
Don't worry about it. Don't worry about it. If you want to volunteer and say you're welcome to, but if you don't have to.
I said chemical.
Okay.
It says it's closed.
Says closed.
That's what it says.
Anybody else get that? I can look, but if I look, people are going to see what the answers
never
were.
mind,
And then it's skewed. All right.
Yeah, mine's
Everybody still working? So what do we got? We've got 78% chemical. 20, somebody just sent something. Now we got 79% chemical and 21% physical. Okay? So now, what I'm going to do is I am going to clear it again. I'm going to give you a little explanation of what's going on, and you'll vote again. Okay? So this is your first example of my horrible drawing. Okay? I have bad enough handwriting. Imagine drawing shapes. Okay? So we've got a glass. Okay? We have water. It's wavy. You're moving or something. Okay? And then you have your filter paper. In the tip, colored black.
It wicks up.
The water absorbs here, and it goes through the whole thing, right? I think everyone probably imagined that happening. When that happens, the water takes the ink with it. Okay? So, what you end up with, if you have the water, and you end up with colors up here. But like he said, what color is black? How do you make black ink?
Every other color.
You mix every other color, right? And so, there is red ink in there, and blue ink, and green ink, and Roy G. Biv, right? But each color is a different chemical, right? A red dye is one type of molecule, and a blue dye is another molecule. And if you've ever tried dissolving something in water, you know some things dissolve better in water than other things, right? I can put salt in water, it's going to dissolve easily. If I put this table in water, it's not going to dissolve very well, right? And so, the things that dissolve well end up here, because they dissolve water quickly and they follow the water up. Imagine I had sand in the tip of that coffee filter. Is sand going to dissolve? No. So where's it going to end up at the end? It's going to stay right here. So the things that dissolve really well end up at the top. The things that don't dissolve at all stay here, and then you have a spectrum going up.
Okay? So, vote again. Now it's basically 50-50. So, somebody who says chemical, still want to defend it. Why is it chemical?
Because you're separating different compounds still.
Okay.
It's more than one,
But it's a mixture.
chemical or compound, whatever, it's being separated into different ones. So it starts out as one or more because it's made of more than one, and it's separated into more than one.
But they're not bound in mixtures.
Now look at me.
They're not bound.
I know the answer.
I think it's chemical because it didn't start out as what it was originally.
But neither does ice go into water or water going to gas. It's completely different.
It's not physical, it didn't change.
This is like politics. I know.
Yeah, but it does change shape.
But fortunately, unlike politics, there is a correct answer. If I just tell you, we're done. So, yeah. Actually, you're first.
You mentioned dissolving, so I guess I would think that because you mentioned that there was a physical change because the state of it, the physical state changed.
Okay. Yes.
I'm done.
Done. Anybody else?
It's a trick question.
I mean, is there
No. There's definitely a correct answer here.
This won't be on the
Isn't it, I
test.
mean,
It's still a coffee filter. And
One of
but it's a permanent change. That color is a permanent
but
change.
it's not permanent
Okay.
if you use another color, you could dye it back to something else.
So,
Is-
go ahead.
Is it the physical or the chemical change of the coffee filter or
We're looking at the colors.
the
And
color?
here's my big argument. Is there anything reactive in Sharpie and coffee filter that would cause it to do anything? Chemically, no, I don't think so.
No, it's only the first week of the semester. We don't know.
I don't think so. I mean, I haven't done experiments on it, but I'm pretty sure if you took a Sharpie and combined it with water.
So,
Can it be bold? Can it become
Because I've had Sharpies
Physical?
and I've written on something and I've gotten water on it and nothing changes really.
So, I said there were some things to look for to figure out whether it's a chemical reaction. What were they?
Color change.
Permanent color
Bubbles,
change.
permanent color change, and temperature change. You don't know whether it bubbled or temperature change, but you can probably imagine it didn't do either, right? But he makes a good point. Here's you, right? That certainly seems like a permanent color change. And when I say permanent, it doesn't, I see what you're saying, you could add another thing, it's gonna change it. But permanent color change implies you can't reverse it. Yes, you can do something different to it, but you can't reverse it. And so, how on earth are you gonna get that back to a black dot in the middle? That seems pretty darn permanent to me.
If you had some kind of weird machine that could.
That's a stretch.
Yes, just stretching it.
It seems,
I still think it's physical.
actually, it's really, really easy. It's really easy to get that back to a black dot.
Oh, yeah?
Oh, you fold it up. You fold it up, right?
You wash it. Heat it?
If you wash it, it's gonna turn white. If you bleach it, you're using a chemical, bleaching is a
Yeah.
chemical reaction.
Do you heat it or?
Could you
Dry it out and maybe it would like.
No, that's dry.
Yeah.
That's dry.
Boil it?
This is gonna be one of those,
You put water in the opposite direction.
put water in the opposite direction.
I'm done.
flip this around, and this is going to move back up to there.
Yep. Okay, cool.
It's physical.
Yeah.
Okay.
It's only the first day.
No, because like he was saying, yes, you start with black and then with colors. But what you started with is a mixture of blue plus green plus yellow. It's like having a mixture of the iron and the sulfur. They're mixed together. But you can easily just pull them apart. You can easily just put them back together. That blue is still the same molecule at the end. It's just here you had 3 different molecules mixed together, and when your eyes see all 3 at once, you see something completely different. But once you separate them,
When you said a change of color, it's gotta be permanent.
it has to be
Nobody
permanent,
can go back.
and you also have to be looking at a single thing. And so that blue molecule, even when it's in the dot of black, that molecule is blue. That one is green and that one is yellow. So when you put them together, your eyes see black. Because if something is blue, that means it absorbs everything except blue, right? So it reflects blue. But this one, the one right next to it, absorbs everything but green. And everything but green includes blue. So whatever this one reflects, that one absorbs. Whatever that one reflects, that one absorbs. And so you get black. No white. So it is a physical change. We know that's not on the exam.
Oh, thank you.
There will be much clearer than that. So evaporation of water, physical or chemical change? Physical, state change. Burning of natural gas. Chemical, melting a metal. Physical, this is a state change. Converting hydrogen oxygen to water. Chemical. Those are the types of problems that you're more likely to see in a class. So we talked about chemical changes are kind of easy to visualize. Chemical properties are a little trickier. So a chemical property describes the ability of something to undergo a chemical reaction. So what would you say about how reactive water is? Would you say water is highly reactive? Depends on what you put in it, but I mean, if I have water sitting here, is it liable to explode on me? No. If I spill it on me, it's not going to react with my foot and dissolve it, right? What about what's something that you would say is very reactive?
Gas.
What kind of gas? I mean, air is gas, but methane gas is very reactive. I think somebody said acid. Acid is very reactive. Gasoline, that's very reactive, right? So how reactive something is a chemical property. It describes how likely it is to react.
That's due to electrons, right? Well, I guess that's further.
Yes, that's a later lecture, but that is definitely due to electrons. So an example of the chemical property is that hydrogen burns very easily when it's around oxygen. Helium is unreactive. Helium won't react with anything. So is anyone familiar with the Hindenburg?
Yeah, made out of hydrogen.
Yeah, so Hindenburg was a Zeppelin, which is basically an old blimp. Okay? Hydrogen, they used to use hydrogen to fill blimps.
Terrible idea.
Imagine a hydrogen-filled balloon hitting a power line. Okay? It doesn't end well. So we now use helium in blimps. Helium won't blow up. You may have a whole town talking in really high-pitched voices for a while, but it's not going to blow up. Helium is unreactive. We'll talk about this later on, but everything in this last column is called noble gases. And they're called noble gases
because they don't want to associate with the common folk, right? They're the ones who drink their tea with their pinky in the air, okay? They're noble gases. They don't react with anybody. They're the best in the world. They can't get any better than me, so I'm not reacting. I'm not changing for anyone. It's like a high school yearbook. Don't change for anyone, right? Do they still write that in yearbooks? Okay. I'm not that old. I just turned 30, but I just turned 30, and I went to update my insurance last night, and I couldn't figure out why my insurance went up. And I realized, crap, I'm now in an old person age group.
30 to 50.
30. Yep. Iron rusts very easily, right? Put iron outside and it gets wet, it's going to rust. But if you put stainless steel out, that doesn't rust very easily. Silver tarnishes very easily. If you have silver jewelry and you don't wear it in a while, and it's not in a protective case, it's going to turn green. Silver is reactive with oxygen. On the other hand, gold is very unreactive. If you have gold jewelry, it takes a long, long time for it to oxidize. You ever heard the word patina? In fine jewelry, they talk about gold getting a patina. It's basically the oxidation. But it takes decades to get a noticeable oxidation. Whereas silver, it can happen in a week. And it happens so fast that it's a bad thing. You have to constantly polish it to get rid of it. Our last topic is the scientific method. Okay? So what we do in lab and in science has a process to it. It may seem like people are willy-nilly putting glowing genes in the rabbits, but there are reasons for it, and they're following a process. What usually happens is you make an observation. You see something, you say, wow, that's interesting. And you say, I'll bet that means this is true. And then you test it. So you do experiments, and you go back and forth, and you get your results of your experiments and say, well, if that's true, this must be true. And once you get enough data, you can come up with laws and theories. So science is a method for answering questions. You find a question, you say, well, what do I already know? If that's true, then I'm guessing this is true, so let me test it. Now that I have this extra fact, let me come up with a new guess at what's going on. So observations are the collection of data. It is simply looking at something, looking at the start, and so I can see this looks, it's shiny, it's reflecting the light, it's probably a solid. I mean, it certainly seems like it has a definite shape. I'm guessing that's a solid. Then I can experiment to get more observations. I can hit it, does it sound like a solid? If I pick it up, does it change shape? If I heat it up, does it change volume? I'm making observations to figure out whether that is a solid or not. Once I make some observations, I make a hypothesis. A hypothesis is a testable explanation. It has to be testable. When I say testable, if you can come up with any possible way, even if we don't have the technology to do it, it is still testable, right? So I can test whether, if I heat that, it expands, right? I can't test whether it can talk. Because if I don't hear anything, that doesn't mean it can't talk. That just means it didn't talk. And so I don't know if it can or not. So a hypothesis is a testable explanation. It is an educated guess as to what something is or why something is happening. A law describes how nature operates always. A law is not testable. I mean, you can show that it doesn't happen, but a law is not up for debate. A law is a law. If your conditions are the same, it will always happen. If I drop this marker, what will happen? It will fall. That is the law of gravity, okay? I cannot break that. Gravity exists and there's nothing I can do about it, right? So that just explains what happens. The law is that when I drop this, it will fall. But that is not an explanation, right? I'm just saying, when I drop this, it will fall. There is a theory of gravity also. The theory is that objects are attracted to each other. This object is attracted to the Earth. And when I drop it, the attraction pulls them together. I don't think that's wrong, but maybe in 5,000 years, someone will prove that wrong. Do you see how that's something you can prove wrong, but you can't prove wrong that when I drop that, it falls. It happened. You saw it. Say it again?
Isn't that being proved by gravity?
It's, the law is proved that gravity exists is a law. But what gravity is, the fact that it's an attraction between two objects, is a theory. We're pretty sure about it. It's probably right. But there are certainly details in gravity that we don't know yet, right? And so that is a theory. People really get laws and theories mixed up. So, somebody give me, well, I don't know if this is on the homework or the quiz or the exam or not, but something I have used in the past is, I think that if I eat nothing but Cheetos, I will turn orange like an Oompa Loompa. Is that a hypothesis, a theory, or a law, or an observation? It's a hypothesis, right? I think that if I eat nothing but Cheetos, I'll turn orange. That's testable. I can eat nothing but Cheetos, right? Nothing's stopping me. I'm my own man. Mom's not going to stop me. So I can test it. Am I going to turn orange?
No.
I think no. But has anyone ever done it?
Eating carrots, turning you orange has been a popular.
Yeah. I mean,
You might turn it down.
why are flamingos pink?
Because of shrimp.
Because of the shrimp.
Oh. Okay, but Cheetos, I feel like that's an artificially colored thing. It's not like a natural color, you know?
But who's to say that's not still going to work?
You're right.
I mean,
No. No.
how many slides are left?
2.
Okay. You ever taken antibiotics and it says don't go in the sun?
No. Yeah. No.
Antibiotics, you can't go in the sun because you get sunburned really easily, because that is an artificial compound that collects in your skin. And it absorbs the UV, and it will burn your skin when it absorbs the UV. And so, what if that antibiotic was orange? And it stuck in my skin? I'd be orange. So what if the orange Cheeto dust does the same thing?
Yeah. But I've had like pink penicillin. That does nothing. That's an antibiotic.
That's one experiment. We haven't tried Cheetos yet, though. And no, you can't get extra credit if you eat Cheetos for nothing but the next week. Okay? I'll give you a round of applause, but no extra credit. And so this is the scientific method. You get data, you look at the data, look for patterns and trends, make a hypothesis, get a hypothesis, test your hypothesis. And you go in the circle around and around and around until you're a lonely grad student and you have to graduate, so you have to come up with a theory for your dissertation, and so you publish it knowing you're wrong, but there you go. You got 200 pages of BS. And so you have a theory, but a theory is not a law. So it's probably BS, so somebody else is going to disprove you. They're going to do more experiments, and they come up with their own BS theory. That's science. We'll skip that. If you want to watch, it's called Elephant's Toothpaste. They mix hydrogen peroxide and yeast, I think, and it makes this big soap, and it makes this big, huge plume of phone. So remember, we have lab on Thursday. Be sure to print your lab. Bring your safety equipment. The homework is now available online. You got a week to do it. I'll remind you multiple times before then. So I'll see you Thursday. If you have questions about anything, send me a Canvas message. That's always the best way to get it. Free printing?
On what?
So if you bring your own paper to the computer lab here, I guess you can print it for free.
Yeah.